嗯，
那个谁可以去认识？
啊，
太长了，
宇航啊，
宇航可以去认识。
他叫你。
你可以去认识的时候，我们班有一个老师。现在我听不懂。我说你可以去认识的时候，我们班有一个。
好，扣着你。
好，我看到这个很厉害的，我也懂他自己讲啊，
重点不要问他，他就
不能接近他，可能爱上你，他也有问题，他爱上你了，就不好，
所以我觉得你，
也不好哎，
所以我说你要去认识一下。
要尊重所是你是给我东西的吗？他是有点恶心，为什么？他人格一点点问题，然后对他来讲是什么？拿 A 减是 fail。但是那个要求比较高。
哦，我到时候问他可能我给 A 级。
然后啊，对，然后还是跟他讲我常常
说到你说他说，然后他手很麻烦。
你还讲不是4.0就是 fail，真是很多人背诵。
我昨天问上期说，我跟你说嘛，你愿不愿意帮我打到一个名人？然后让上期问我说，有没有现在约？
女人弟弟摆还这样很爽。
我不是故意。哦，我昨天
是差一点点啊，他摆的好的。
他昨天在帮他的 FYP 老师做东西嘛，然后我说就想我帮你打2篇东西嘛，然后他的 FYP 老师给他钱了4年。你是不是应该反思啊？
我这有钱，他有 grant，我的老师拿不出来。grant 的话，那
所以没关系，就应该让学生帮你干一个。
没有意外，
你可以上好大学哦。
因为你看，if y is defined in x t 嘛，所以 find the
你这个翻译什么意思？
I'm right。
你知道什么应该是你可以理解成是个点分散。I mean, A and spec off is secondary。
它会有差别的。
有啊，它两边就会上些有一个 s p e 的。
嗯，真的可以分。
就是变成每次对不对？
不太一样。 那个读的东西，得要
都比较少。
我全部雷马路咪，
嗯，哎，这种人很谦虚，是不是？谦虚的那个连麦要发名，叫我名叫做那
对，原来没等见，不看等不看等见，对干嘛去了？啊，去哪？
什么东西来着？写词不？
哎，特朗普要去中国了，是吧？是的，对啊，好，这个很好，这个股票要上了。哎，好的，这个答案。这个可以的。
So last time we talked until here, and then this one is a proposition. And then there's a unit ring homomorphism from integer to any ring. And we the proposition by define the map by sending n to n1, and we check it resolve addition and multiplication.
You know, like the definition of n times one identity. Right?
Yeah, got many ones.
How many?
And n times.
Yeah. So the bottom is just n plus n times of identity, and then it's split out.
So the map is completely determined by where one's goes, and this show that integer is universal. And for the properties of homomorphism, the unit are preserved under homomorphism. And
Oh, I think when you write the proof, right?
Yeah.
You can actually write it properly by I think you're missing one step, right?
this is just a proof idea.
Yeah, I know it's proof idea, but almost it's a proof already.
Mm.
So you just missing one step is like, how do you do the first equality? Y is equal to 5 times. This is homomorphism, right?
Yeah.
So property of homomorphism.
Mm.
You can combine the terms in the domain.
Oh,
So it's
okay.
equal to 5u times u inverse. And u times u inverse is second. So it's 5. Yeah. Actually, this proof is very short. And then it's a unit, right? So you need to. This unit is the two-sided or two-sided, right? There's the inverse on the left hand.
I think it's two-sided.
Yeah.
Yeah.
So you need to show the other side, left and right, is where you just change the position of u and u.
Yes.
And this proof is very straightforward to write out.
So I continue. And then the example is zero divisor are not preserved. And then we give that the 2 in integer is not a zero divisor, but becomes 1 in modulo of 6. For the 2.3, the kernel is all elements mapped to 0. And next one is a proposition. The homomorphism is injective in if and only if its kernel is 0, and then the phi is injective. So here's the proof. And the definition, a subring is a subset closed under operation and contain 1. In rings, epimorphisms are not always surjective. For example, the integer implies the rational number.
Can you explain like why is it not FEM?
Sorry?
Can you explain like why the vector is not a FEM thing? I mean it's a
You mean the example?
I mean how to show this map is a happy motif.
Okay. The epimorphism in a morphism that is right cancelable.
Right cancelable. So what it means?
Maybe I don't know this.
I mean you can just write out your case.
I didn't prepare the case.
You didn't prepare the case. Then you didn't prepare, you also need to ask using this case. Because I'm asking about this case. I don't really care whether you prepare. You have to work it out now. Your boss is like that. Your boss is worse than your boss can fire you. Just try it. Just try and see. Start over.
You mean the
Check out. Just check properly.
example? You mean the example?
Show that it is a female.
I don't know how to show.
Write down the FPM of figure definition. Down the FPM of figure definition. You define it?
I think I didn't.
Then how
didn't
can you talk about it? You should define it. I think we did it for separate. You have to define first.
This one.
Uh,
Go on, this. Fly.
you mean the integer example? Oh, okay.
Your app is F2.
Okay.
You want to explain?
apply of Teoh. 你写出来的，
你写出来了，现在 shepherd display。
你拿去 apply of Teoh地方。
You know that ng2 is in the integer.
Okay.
And so they agree on integer. But the rational number is also determined by integer. And so the ring homomorphism must fulfill the inverses of unique. So the map fulfill on the integer, so they are forced to agree on origin.
Okay. Right. So this is no explanation, right? This is just reading. Maybe one thing you need to know, I think up to date, ChatGPT, not just can produce notes, they can produce a lecture video, a paper to explain stuff. So I think if you got a chance to present, you should try and learn. So how to present? Usually, one technique you should learn is try to fill in as many detail as you can. Because sometimes the detail is hidden inside the sentence. So sometimes it's worth that maybe you can write more. But before that, you should understand what you write first. Yeah, so this is the most important thing. You need to ask yourself, do I understand what I write or not? Okay, so just now, why I laugh is because I thought you say you haven't prepared. Why suddenly there's a conflict proofing?
Because just now I asked, is it about the example proof? And then you said that I need to prove the definition of
Yes.
the epimorphism.
So actually you prepare.
So I only prepare the example.
For this example.
Yeah.
So you mean you actually prepare, but you thought you haven't? Okay. Good. So this is something you learn on the spot. You suddenly realize that, oh, actually I prepared this. But then you do you know what you are writing here or not, actually? So maybe, okay, I use this notation. I follow your notation. Okay, so what you do is it's better that you write, suppose F is this inclusion method. Okay, and then I want to show that F is dimorphism. So suppose that there are two maps, right, going up from Q to somewhere. Do you mean real number or ring here?
Ring.
Ring. Because sometimes I see you write this R, so I don't know it's the same R. So why they write like this? Actually, this is just a G composed F, G1 composed F. This one is G2 composed F. Okay. Maybe I should put it up here so that they're equal. So that means they agree on the integer. This one, I think, very clear. But then how about this one? But every rational number is determined by integer, and then ring homomorphism but must preserve. What does that mean? Preserve inverse of unit. So meaning, if you know that they agree on these two things, they should agree on this as well. What? It's a ring homomorphism. So you need to write down what's the definition of ring homomorphism. So you need to expand this a bit. Huh? So this one is in Z, right? This one is in Z. A is in Z. So these two things is the same already because I know this by assumption. But then this two is different thing. This one is in Q. This one is in Q also. But still you need to like relate back to the integer, right? So how do you relate back to integer? G2B inverse actually is equal to G2 on B and then take inverse. This is what this means. Must preserve inverse of the preserve the inverse of the unit. Then this B will become something in Z. Again, here agree with this G2 B inverse. So this one agree. This one also agree. So the two sides agree. So that's why this one agree. Okay. So this one equal this one. Does it make sense? That's all you see. You write an English sentence word, it means so many things inside mathematics. So you need to really get this process up. Understand? Make sense or not? Yeah. Yeah. Okay. Yeah, try write down in your notes. You know you have to type it out.
Yeah. So for the 2.4, the product of ring is defined component wise. And for the remark, product of fields is not a field.
Can you give example?
but they're tricky. And then they want to know.
Uncross argue.
Yeah, cross line is tricky. Cross line. 1-0 is not easy. never 是
那个，
我一开始是想，然后我想想，哎，不太对劲。
我一直在想那个 simplicity 的问题
Simplicity
是 much 的是吗？但是也不对，还有那个
zero divisor，
就是这个女孩子，他玩之后看 C 1之后就
有想法吗？
嗯，是
Yes
是，
啊，explain 啊。
嗯，So one of the criteria of Q, if AB equals 0, then either A or B must be 0, but for this example, two non-zero element get the 0 element.
Why few have to satisfy this?
Because of the 0 divisor.
Yeah, what? Yeah, why few I need to check on zero divisor?
You mean why few need to fulfill?
What's the definition of a few?
Okay.
I think the definition of a few doesn't involve zero divisor.
But then 可以 contradiction.
Oh, it say the product of two field. Like this one.
Mhm.
Facility says
It will fulfill this.
Okay, so my question is like why the second statement is true, right? So you need to come up with two field and then show that it is not a field. So to show that it's not a field, they need to show that it doesn't satisfy the field property. So what's the definition of a field?
So can you repeat again?
Repeat again. Okay. So what's the second statement? If you have two field and then you take a product, might not be a field. Okay. So I'll give an example. So I ask you to give an example.
Mm.
So what's the example you give here? What's the
So,
two field?
These two are field and then
This is not field. This is just an element in the
okay,
field.
element in field.
Yeah. So what's the field we are talking about here? Maybe real numbers and real numbers, right? Okay. So to say that something is not a field, obviously you need to tell me which property doesn't satisfy, right? So what are the property of a field? What's a field? Basic question. You should look at your notes, man. I thought you introduced the notes. Where the notes? Introduce to us, right? What's a field? You go backward in the slide. Yeah. If you cannot find it, that means you are missing something. You have to go back again. I think it's somewhere after ring. Yeah. Hey, wait, not yet, not yet. Wait. See, this proposition, you see this proposition? R is a finite. Okay, this one is finite. Never mind. Don't care about this. Okay. Go backward. Oh, yeah, this one. Remember, you asked us to remember one. Field implies integral domain. So do you know how to prove this?
Mhm.
So what you have done is you show that it's not an integral domain because there are zero divisors. Okay.
Yeah.
Okay, so this is the relationship between field and zero divisor. And then your notes says what? A field is a commutative ring with identity such that A times A inverse equals to 1. What's this? It's not complete. For all A, there's non-zero that exists inverse. I think there's something missing here. Have we defined it before? Can you go? Yeah, this one. A field is a non-zero commutative ring in which every non-zero element is a unit. You see, inside these terms, there's no zero divisor, So how can you use zero divisor to explain this definition? So you need to tell me the relation. The relation is the next one. Field imply integral domain. Integral domain is defined using zero divisor. Okay, ma? Okay, ma? So the moral is this. I don't care you graduate, whether you know field or you know integral domain or not. But then this logic, you have to hold on in your career. You understand what I said? You cannot, people ask you one thing and then you use the other thing to explain and then didn't tell people what's the relationship between them. This is the thing you can transfer. This is the skill that you can transfer. You understand? You tell your customer integral domain, they don't know one. But then they can understand whether your explanation makes sense or not, you know. You can see the logic on it.
Yeah.
Can see?
Yes.
Okay. So another logic from here, let's say I don't know what's the relationship between field and integral domain. You should also like figure out from this equation, right, that it is not a field. Because you need to understand what the field is. A field is every non-zero element is a unique. Is a unique. So that means what? Let's say you know this is true, right? Okay. So I can multiply and inverse here. I don't know, I don't care what's the inverse, but then I can multiply and inverse here. Then what I get is 1 times 0 1 equal to 0 0. Then what I get is 0 1 equals to 0 0. Contradiction. Okay. Without talking about this also. You understand? So sometimes some concept you don't need to throw in special terms. This one easy to understand. Why? I just need to know like how they multiply. That's it. You don't need to tell people zero divisor. But I just use the field definition here. Then this one you cannot like run away one. You understand? Okay. I think this is a common mistake that people like to do. They don't understand about one thing. They try to explain using the other things without knowing what is their connection. I got one student in my undergrad class also like that. He cannot argue with this point already. Suddenly he throw new points into it.
Yeah.
又扯另外一个东西进来。Actually, this is how people argue, you know. They try to like switch your focus.
鱼肉吗？看到。奇怪。
Okay, yeah. Usually these will lead to endless of argument because you are not arguing on the point. 你只拿新的观点进来嘛 ？OK 吗？嗯。
So for the 2.5, NG form a ring under addition and composition. And for the proposition 2.6, the endomorphism integer is isomorphic to integer. So
What's the notation AB then?
Abelian, yeah.
Wait, what is AB? Endomorphism is a map from Z to Z, and then abelian means Zorn.
Or category of abelian group.
Category
Category of abelian group.
of abelian group.
Yeah.
Maybe it's kind of what we feel.
Reason from Z to Z.
Do I need to explain anything? So the whole thing means the all group homomorphism Z to Z.
Okay.
Yeah.
Yeah.
So I continue. So we have done some proof. So the every homomorphism is determined by A1. So AN equal to NA1, and we define the map phi A equal to A1. So in conclusion, this gives a bijection, so the rings are isomorphic. So for the proposition 2.7, we define lambda R implies the endomorphism R by lambda Rx equal to Rx, and And for the proof, we define the lambda r implies so the next one proof we show it preserve addition and multiplication and identity. So final conclusion is this map is an injective ring homomorphism. Yeah, that's all my presentation.
原题吗？没有，有在听。就OK。不知道 A 跑出来 A 是什么东西？比如说哪个 A 啊？前面很多 morphism 有一个 A，他说有 A 吗？
有很多个 endomorphism。
是小小个在下边的
啊，对。
用那个来比
subscript
啊，
加边页。
因为 like other noting abelian group，
相当于是后面
其实不要放也可以这个 case。But then 那个 author 是讨论比较 general 的，其实它是 NABGG。啊，对对对 ，OK，哎呀，G，
就 NAB 相等于后面
耶，哪个 A 啊？你讲哪一个 A？那里有 A 啊，alpha 哈，alpha 有个 N，是什么啊？Yeah，哎呀，这个 A 是什么啊？
像是
alpha 是什么？alpha 是什么？
应该还是你要证明那个
就是
没有啊，然后是 animal 里面左边的 animal
哦，
啊，A 是什么？啊，Yeah，right，你 alpha 从哪里来？要写一下，alpha 是谁来的？
也是这个
这个是什么？它是一个 map from，
integer to integer。
对咯，说它是哪里的东西？哎，看你的键哦，看你上面那个 note。
A 是 integer。
在哪里来了？你看，
就是 for some fixed integer A。
应该不是随便 fix 的，它不是随便 fix，它是那个 alpha one 来的，对不对？是那个 alpha one 来的。Well，来这个 map，这个是一个从这个东西是在 n，你的这个 n A、B 在里面。And then 呢，你要有一个 map 去 set，and 这个 map 是来 evaluate 这个 function 在 alpha one，在 one，然后这个是 define by 你的 A。then 你的 alpha n，因为它是来 add up 这个 one n times，but then 你的 alpha is a homomorphism，so actually 这个就是 alpha one n times，so 变成 n times 的 alpha one，so alpha one 是 a，所以这个变成 an，这个是你的这个东西来 ，OK OK，yeah，I think 还是那个问题还没有解决，就是你写下的东西，你还是不是很清楚。But then 我觉得可能跟你的性格有关系，你是不是很容易相信人？不相信人，不相信人？Why？你写的东西你相信吗？
嗯，
我不相信
因为
啊？什么？
可能
啊
我这样做的
，It's okay，but then 你要 to be honest 出你自己嘛，就是说我是不知道这个东西，但是你要 try to 去知道啊，要不然的话 no point 嘛，你来这边，你不知道回去又不知道，毕业了又不知道的，不是浪费钱。So I mean like 一点一点学啊，你可能学不到100%，但是你至少也要来学一点点嘛，一定要 more than 零嘛，epsilon greater than zero，你一定要学 epsilon 嘛，你学 epsilon 再学多一点 epsilon 啊，对，多一点多一点，不用紧的嘛，不要讲我有目标一定要学，不用紧，我们多一点就好。但是比如说今天从上个礼拜到今天还是一样，人就没有 epsilon 了啊，对啊，一点点，至少要有一点，有啦，有一点啦，我看到一点了，就这一点，再多一点，慢慢多一点，多一点，哎，你就很不一样了，其实，OK 吗？这个是
就是
我到一样了，OK，
太压了。
你干嘛呀？
哎呀，慢慢来，没有啊，我不觉得我今天也能讲完啊，但是只是因为我想要一天给你讲完。
不要急，不要急。
今天讲不完了，
啊，但我觉得今天讲不完，我真的会慢慢来啊。
你可以讲学。
等下会讲，敬请期待。按12月讲，好像有稍，第二次应该有比较好了吧？第二天走，如果第一天有点讲到，第二天那边就掉。
OK，Thank you。
有一层还可以在环境。
聊一层。
你肯定那个什么，你们都不知道吗？那我来写给你看吧。
有吗？没有吗？
有，
哪有？
有。那时候seminar的时候，那个算那个题目的那种，题目我的，被问出来那个，然后你问了，题目来就，然后你就讲，这是个简单吗？那我来算给你看。
怎么还有我夸张？这人就整天丑化我的形象。
我那个手画很挺很亮。
那我应该说你呢？说你还跟他讲过。
对，我现在很不舒服。我等下去找哪个地方讲？
我是现在还在休息一下先。
啊，
你在5分钟，然后这地方挺好。我们不是已经修了感觉有5分钟。
没事。
没事，没事，这个方面。
可以切干嘛干嘛？对，你看你在很少力了。不行。
都是
上面有听过比赛，
seminar的时候，
他很 heavy on motivation，然后 super
有在那个Algebra
超级 heavy。
他不是跟那个谁一样？ motivation 可以弄让你很的神，结果一听到那个这东西就，门槛就远了。加这个 MS，怎么来说？目标性哦，还要找那个结尾啊，因为我不知道你有看到他的那个 intentional report，有一条题，看一下，
我这样 send 给我一下。
那取水不到，虽然很公平，像中之间没有说东西。
他真的意义上把那个市场给别的东西放进去啊，还要给你看历史。
那有没有学到什么装的嘛？他应该是不是傻？因为他没有他们的公司做得到，他们的公司是确实有这样的系统的。
但是问题是，他把它 phrase 很重。
我让你能，我让他教出来，让你教出有东西。
本来有没有来？你们不是有方法教的？
有，这还有国家，他们的知名度很强，所以他不能一登进去还要推你，
哦，他不给你教。
还要推你，有当时他才能讲。你真的是来2个月吧，还不会。
不是你 cost 你。
对呀，装。
Shall I start now?
要上。
Okay. Hello everyone, it's me again. Today I will start talking at the beginning of my presentation. I will stop talking about ring theory for a while, and I will talk about some set theory first. The reason of doing so is because I want to introduce an interesting result in set theory called Zorn's lemma, and I will use this result to prove the existence of maximal ideals for any non-zero ring. And after that, I will discuss about a property on polynomials, which is called primitivity. And lastly, I will give an idea on how to construct a field out of any integral domain. So without further ado, let's get started. First, I need to introduce a few definitions first. First, definition. And order relations I denote by this symbol, a curve less than symbol on a set Z. Is a relation satisfying the following properties. So it satisfies 3 properties. Okay, first, it's reflexive. And second, it's transitive. And third, it's antisymmetric. Reflexive means that for any element in the set Z, we have A precedes A. Transitive means that if A precedes B and B precedes C, this implies that A precedes C. Antisymmetric means that if A precedes B and B precedes A, then we must have A is equal to B. So let's have we have 2 simple examples. For example, the inclusion relation on subsets of a set. And also the usual ordering on the set of integer. But there are a significant difference between these two. If you pick any two integers, either it is the case that either one is greater than the other. But if you pick any two subsets, it may be not the case that a subset is the subset of the other. So this leads to a different ordering, but I forgot that I need to introduce. So if a set is if it has an order relation, call it a poset. So in this case, Z is called a poset. Poset stands for partially ordered set, but this is the abbreviation of that. So for if you require any two objects to be related by the order relation, we have another definition, which is total order. A total order is an order relation on a set Z such that for all AB in the set, either A precedes B or B precedes A. And we have a notation if we use without the straight line to denote the case where A precedes B, but A is not equal to B. And a set with a total order is called a chain, not a poset, but a chain. So if the ordering on that set is satisfy this additional requirement, we say that this is a chain, which means a totally ordered set. Okay, next is a chain. Why is called a chain? I'm not sure about why the nomenclature is a chain.
Because if you draw out the order relation, it forms a chain.
Yeah.
That's why, when I first picked up the Algebra one, the responsibility of the chain. 什么叫我刚刚拿你换的是不是这个是你说你知道是高斯的chain为什么是chain？高斯的就的chain。
Another two definition. And an element M of a poset that
It's the order relation, people call it partial order.
Yeah. I noticed this, but the order define it as order relation. So this is a total order and this is a partial order,
Yeah.
but the author defines it as order relation only. Yeah. Then like the naming, it's
Then if you put partial order, then your poset makes sense.
yeah. But I follow the textbook, the word used by the author. So an element M of a poset Z is maximal if for all A in Z, if A comes after M, then it must be the case that A is M. The definition of maximal, basically, it is saying that nothing comes after the maximal element. It is not the same as a maximal element. Since if you say that an element is a maximal element, we say that it comes after everything. But since that we are only saying that Z is a poset, so it may be the case that some element is not related to the maximal element. So yeah, that's a difference between a maximal element and a maximal element. Next, an upper bound. And element U of a poset Z is an upper bound if for all A in Z, M comes after U comes after A. So U is a maximum element. Okay. So we have now introduced two order rings. One is called a partial order and another total order. We have actually a third kind of order, which is called well ordering. So well ordering, we build this order on the definition of total order. A well ordering on a set that is a total order such that every subset of Z has a list element. I believe that these definitions are not unfamiliar with you. Okay. If Z with this with an ordering, we call this set a wall set. It's a wall set. Yeah. Stand for well-ordered set. So we have a whole set, a wall set, and a chain. Okay. So what is interesting about well-ordering? For example, if you want to think of an example of a well-ordering set, like the most simple example that I can think of is the set of positive integers, like the set of natural numbers. If you pick any subset, you always can find a list element. So this element is defined to be if A is a list element, that it comes before any element B in the set. So the set of natural numbers is an example for a wall set. And if you think of natural number, we can use principle of induction on natural numbers. To prove a property that is true for all natural numbers, you can use the principle of induction. But this is not specific just for natural number, it is for any wall set. So we have a property we call principle of induction. So suppose Z is a wall set, and we let S be any subset of Z. Then for any element in Z, if for any B that precedes A, or any B that precedes A implies that B is in S. This whole thing implies that A is in S. Then S is equal to Z. This is a generalized version of the mathematical induction that we have used to. Any questions about this?
Or you can ask for the list element.
This element, okay?
I mean, the induction also needs to satisfy the list element is true.
Yeah, but since that this if A is a B is a list element, then this is recursively true. So this is true, and this is true. So S is equal to Z. So it's because that for any list element, this statement is recursively true. So it's implied in this whole sentence. Can you reply?
Suppose that is a set. This element is a so 需要做我本来在什么时候需要这个 list element 比较特别注意。
哦，
他说是这个。
What's the question again?
I'm just asking if you need to specify that things that I think that's
Suppose that is worthless or anything. Then, oh no, this is just a property.
Notation for any A in Z.
For any A in Z, if we have if B precedes A implies that B precedes. No, this is sorry. Oh, sorry for the mistake. So if B precedes A implies that B is in S for all B. Sorry for the notation.
Because you take the least element. The least one is or knowing.
但是因为我是要做你当时我们需要特别 specify is in S 嘛，所以我在想是不是需要 specify that is in S。
This is I haven't proved that this property holds for a word set. I'm just saying that this is a property, and I haven't proved that this holds for word set. Yeah, maybe let's look at the second part first. I'm just stating a property. This is how the author presents this idea. It's maybe at first I'm also confused about this introduction. Is we suppose that Z is a word set. Perhaps what the author wants to say is that suppose Z is any set.
If the least element is not there, then all the other elements. I think what he says is okay because there's nothing smaller than this element. So the first part is so then this element.
因为如果你想往这边有些问题这样子啊，set 是意思，都在这里，是什么？
它的 S 好像不是 arbitrary 的，它的 S 是要 satisfy 那个
Yeah.
property 的。
只要
但是我的意思是我们写 n 的时候，我们会上面加一个意思。
I think that
就是说它这个 property 已经包含就是因为前面一段是 reversely true。
So sorry, I think that I didn't add this sentence, so it's quite confusing. S is a set with this property.
Yeah.
Sorry for the. Thank you for the reminder.
它不是随便的。
Yeah. Okay. So, maybe we can prove that indeed, if that is a word set and any subset with this property, we can prove that this is true for any word set. So maybe we can prove this. So again, let the principle of induction holds for any word set. So okay, so suppose that I will prove by contradiction. So suppose that we have a proper subset of Z such that this property holds for that set, and we will proceed and show that there is a contradiction. So suppose that let S be a proper subset of Z such that that property holds. Since that S is a proper subset, so the complement of S in Z is non-empty. Thank you. It's non-empty. If this set is not empty, and since that Z is a whole set, then T has a least element. So let A be the least element. So suppose that for all B that persists A, since that A is the least element of T. So if you have an element that persists A, it must not be in T. So it must be in S. Okay, but we have the property that if this is true, then this is true. S has this property. If this is true, then this is true. So this implies that A is in S. But we assume that A is in the complement. So this is a contradiction. So principle of induction holds for any whole set. Okay. Okay. Next is. So what's interesting about the principle of induction? Whole set. Principle of induction holds for any whole set. So if you kind of find a way to make some set to be well ordered, then we can apply the principle of induction hold to any whole set. So for example, if you have an uncountable set like the set of real numbers, if you find some way to well order this set, then we can, in a sense, apply the principle of induction on a set of real numbers. And the following theorem says that this is indeed true. So we have a theorem called well-ordering theorem. It states that every set emits a well-ordering. What interesting about well-ordering theorem is actually it's equivalent to a thing that we are familiar with, the axiom of choice. Axiom of choice states that initially I decided to prove all three equivalents, but I think that that's not the main point of this lecture, and it takes a lot of time, so I only prepare one equivalence on. Basically what axiom of choice is saying is that if we are given a family of subsets, we can pick a single element from each of these subsets and form a new set. And so if you assume that axiom of choice with the regular Zermelo-Franco set theory to be true, then we are also assuming well-ordering theorem to be true. And yeah. And what's interesting about it is because axiom of choice, these two statements are equivalent to the main point of today's topic, Zorn's lemma. These three are equivalent. So what's Zorn's lemma? So suppose that we have a whole set. If any chain of Z has an upper bound, then Z has a maximum element. So we are using all the definitions that I introduced just now. A poset is a partially ordered set. A chain is a totally ordered set. An upper bound is an element in the set Z such that it comes after every element in Z. And maximal element is an element such that nothing comes after it. Okay. So these three are equivalent. So if you assume one to be true, the other two are also true. I will only show well-ordering theorem implies Zorn's lemma. I will only show this direction. Okay. So let's look at the proof. Zorn's lemma. So if suppose that we have a poset, let Z. This is the curved version Z. No, I use the normal version to denote this. Let Z be a poset. And suppose that any chain of Z has an upper bound. Since we are assuming well-ordering theorem to be true, so we can let Z to have a well-ordering. So I use this one. Let this to be the well-ordering on Z. And I define a function f from Z to the power set of Z by fa is equal to the singleton set. I send it to the singleton set if A union B precedes A. This is the well ordering. So don't be it may be confusing since that we have two orderings right now. This is the partial order and this is the well ordering. So we are using the well ordering here. FB is totally ordered by the partial order. And we send it to the empty set if otherwise. So if this is not totally ordered, we send this to this.
Wait, how do you define FA by
yeah, I will discuss that later. So I will prove that this is indeed well defined later. Okay. So basically, what?
Why you ever tell me what is FA, then you define what's
Yeah.
FB.
Maybe we can show it later. What I mean is after I explain what this function means first. So basically, this function means that since that we have a well ordering on Z. So suppose that we have A0, A1, A2, A3, we can use this function to check if we put A0, this element into our set, is this still a chain? If it is, then we keep it. And we move to the second element and we check, is this if we add into our set, is this the new set is still a chain? If not, then we discard it. If yes, then we keep it. And we run through the whole deck. So just now Kishan asked a good question. Is this well defined? Since that we define a function using the function itself. Yeah. So it's quite bizarre. And maybe we can try to spend some time to show that this is well defined or not well defined. Maybe we will see. This is the well ordered. This is well ordered, this is partial order. So I think that maybe I use a different color will be better, maybe. I think this one use blue. Maybe this blue. This blue. And the other partial order I use red.
Purposely like missing the straight line.
Yeah,
Horizontal line.
yeah, no horizontal line. Just now I say that if I use this symbol, it means that these two are not equal. Because we need to check this, we use FB for all B comes before A. We need to check. And FA, we are defining A, so this is already defined. Maybe, since we haven't checked it yet. So, okay. So suppose that T is a non-empty set such that F is not defined. Let me check. Okay. Since that we have a well order on the set, so we have a well order on the set T. So there exists a list element A in T. Suppose that we have B, this is A. Since that A is the list element, so B must not be in T. So B has to be in Z. No, be in the complement of T. So B must be well defined. Since that we assume T to be a not defined set, so the complements must be the set where all the elements are defined. So because A is a list element and B comes after A and comes before A, so B must be defined. If B is defined, if all B that precede A are defined, then this is defined. So FA is also defined. Okay. Sorry, this one must. Okay. Is it okay? Any questions?
I think the interesting part is when B is like, for example, let's take Z. I think the interesting part is when Z has a well-ordered ring, and then you look at where the list element go first. So the list element actually always go to the singletons.
Yeah, because
the union is empty.
this
There's nothing smaller than.
you mean the this element object?
So I mean, like apply F to the list element of the well-ordered ring. That's the base case.
Yeah.
So if you apply the list element, you will send to the singleton set.
Yeah.
That's because that union would be empty because nothing smaller than it. So actually, you are just ordering one element. So ordering one element is obviously a proper order.
Yeah. That's exactly the point. The first point must be in this one, and anything that comes after that is naturally well defined. Yeah, that's the point. So,
So you finish.
is it okay? Any questions?
I mean, like, so I mean, like, yeah, I mean, like, yeah, it depends, but then, For me, that I would just say when I define this function, I'll say that this definition makes sense because if you look at this element, it's defined there, and then for the rest, it will be like actually this definition is what do you call it, recursive.
Yeah.
Recursive definition. Yeah.
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 It write the base case.
Yeah. Base case. Yeah. But actually, that definition include base case inside.
Yeah.
If I explain it, I will send it for some.
Oh.
So that people won't get confused.
Okay. So we have defined a function and later. So now let's move on. This is the first section. Verify that this function is well defined. And now we let S to be the union of anything that we have collected. And I want to show that this is a chain. Since that if you find a chain, then every chain has an upper bound, we can proceed with the proof. So is this a chain for a set to be a chain? We need for any two arbitrary elements, they are related by the order relation of the partial order. So suppose that we have AB in S. AB is in S. It implies that A is in this set. Any B with A FB. Is this clear? It's so A is definitely in A and B comes before A. And since that B is in S, so B is already defined. So B must be the singleton set B. So B is also in this one. This is the chain that we are constructing, and we construct until halfway, until A. And so AB must be in this set. And this is the full chain, not full chain yet. We haven't proved that this is a chain yet. Is it okay? If no questions, then since the AB is in this, and we already assume that this is totally ordered by the partial order. So A and B must be related by the partial order. Either A precedes B or B precedes A by the partial order. So which means that any two elements in S, it must be related. So S must be totally ordered. So S is a chain. Since that AB is in this and this set is to be B as a index here.
Must be fixed two element in there.
I think that if you want, maybe we use C will be. Oh, sorry. I assume I jump a step. Without loss of generality, we assume that B precedes A. Sorry. I assume this one, since that A and B in S, and this is well ordered, so this is a total order. So either we can assume A, B to be two distinct elements. So either B precedes A or A precedes B. So in this case, without loss of generality, I assume that B precedes A. Oh, thanks for the reminder. Okay, let's go through it again. Maybe so if this is the case, maybe I can use B. I use B, okay? Not okay. Okay, so
You cannot.
since that B precedes A, and A is definitely in this set, and A comes after B, so since that it survives this function, so FA must map to A, the singleton set. Okay, and A, so this set is well ordered and it is totally ordered by the partial order. And this part contains every B that precedes A. And since that we assume that B is in S, so B survives the function F. So B must be in this part. So what means that if I send A to this one, it survives. If I send it to the not empty set, then it means that if we add this point into our chain that we want to construct, it makes the chain not to be a chain anymore. So we discard it. You still can't see B why B is in here.
Still here, you should be another index of.
Yeah, it's okay. Is this better? And since that B precedes A, so B is one of the C's. Yeah, maybe I think this notation will be better. Okay. Okay, so and see that this set is totally ordered by the assumption. It's totally ordered by the assumption, ordered by this assumption or construction. X is the final thing that we construct. Oh, again, sometimes A in Z. Sorry, oh, Z is the whole set. Thanks for pointing out. So basically, S is the final product of this function.
The image.
The final product, yeah. And we want to verify that this is a chain. So if we take any part, if we have a well order A0, A1, A2, blah, 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 if we would take this, and this is totally ordered. We take this, and this set is always totally ordered. But we don't know that if you pick everything, is it still totally ordered? So this is why we want to verify that after we take the union of every element, it's still a chain. But if you take any part, it's still a chain because by this construction. Okay, so we already verified that S is a chain. Before I proceed, I need another result. Let S prime such as Z and X prime is maximal totally ordered set or chain. Ordered set. Then, sorry, it's a totally ordered set. Totally, then S is equal to prime. What I'm saying is that I claim that S is the maximal totally ordered set by the inclusion, the subset relation. And the existence of such set is guaranteed by the Hausdorff maximal principle. And this Hausdorff principle, actually, it is equivalent to the Zorn's lemma, which means that it's equivalent to the axiom of choice and the well-ordering theorem. It's another formulation of the same concept, the same thing. So I want to prove this right now. Yeah? S? Yeah. My S is this one. The union of all FA. And
so you're trying to prove it?
This is a claim. I want to prove that the S that we constructed is the maximal totally ordered set by the inclusion relation. So suppose we prove by contradiction. Suppose that we have a S prime such that suppose that we have a set S prime and its S is not a proper set subset of this one, so this is not empty. This is bigger than this one, so it's not empty. If this is not empty, then do I need the list? I don't think that I need the list. Okay, it's not. So since that this is not empty, we can let A inside. We have an element inside this one. But what does it mean that A is not in S? If A is not in S, that means that we discard it during our the valuation of our function. So F A must be the empty set. And also note that if we take A union with any B, or maybe we use it's okay, use B. B that precedes A and B, then this is the subset of A. This is the subset of, let me double check again. This is the subset of this one. Since that A is in this one, and this is, we collect all B that precede A, so it's the subset of the S. And this one, since that A is in S prime, so we union this, we get S prime. But S prime. But since that we assume that S prime is a totally ordered set, so yes, a contradiction. So FA must be sent to A. Oh, the reason is like this. Since that S prime is a totally ordered set, and since that this is a subset of a totally ordered set, so if this is a totally ordered set, then A, you must send A to the singleton set. So we have these two. So this is a contradiction. So if we have a S, S must be the maximal totally ordered set. Okay, so right now we want to Zorn's lemma. So this is a chain. So we want to find suppose since that by the assumption of Zorn's lemma, we assume that every chain has an upper bound. So we let M be the upper bound of the chain. Now I claim that M is the maximal element. So if M is the upper bound of, so suppose that we have an M prime that comes after M. If M prime comes after M, this implies that, let's consider the set S union with this M prime. Since the M prime is larger than the upper bound, so it means that it's larger than all elements A in the set. M is an upper bound, and upper bound is larger, comes after every A in the set Z. And we assume that M prime is larger than this one. So M prime comes after all A. So if we put M prime into our set, any two elements
that A has one in the set.
For all A in Z. And let me verify.
嗯嗯
Maximal, Zorn's lemma says that the maximal element is for the whole set Z.
What prove that is
sorry again.
so you cannot assume
For all A in S, put catch. For all A in S, so all element in S is so M prime is larger than everything in that. So this is also a totally ordered set. And this must be S. Since that S union M prime is still a totally ordered set, since that every element in S precede M, and we assume if M prime comes after M, so it means that
so M prime is from Z.
M prime is from Z, the set Z, and we assume, remember that if you want to show that an element is a maximum, we need to show that if for all M prime comes after M, we need to show that M prime, which means, this comes from Z, and for all A in S, M primes after A. So if we include M prime into our, so if we include this to S, it means that this is still totally ordered. They are related by this relation. Okay. If S is equal to S union M prime, it means that M prime is already in S. So it must come before the upper bound M. So this is by this and this one, we get M equal to M prime. So this M is the maximum element of the set Z. Okay. So basically, this is the proof for all in okay, so that's the proof for one direction. I still have 6 minutes, but I only have one more result to show, or maybe next class. Sorry.
这个我们是来做模的，
还是这个那种
你说这种什么是拿来做什么？就我们其实重点是要用这个来 prove 说每个non-zero ring 都有一个 maximal ideal 是存在的这只是一个
I think 在那课本里面，它只是一个
extra 的东西咯。
其实这个也不需要也可以。
反正讨论也是好的，因为 undergrad 时候我每次来是，水，你知道为什么呢？你知道为什么排那有一个对了是因为有
OK，
好了3%，对。为什么是用口罩？为什么是会去公司？因为我是以前因为有一半做粉丝做完了很讲 VIP 我已经做完了，他讲这个我给死了，
很厉害。
还没有死。厉害放在这里。